This is the FlowViz Lab by Annie, Grigory, Lou, Eric, and Jose. The purpose of this lab is to explore the concepts of boundary layers, vortex shedding, and Reynolds numbers through flow visualization using smoke and a laser. As an object moves through the atmosphere, the gas molecules of the atmosphere near the object are disturbed and move around the object. Aerodynamic forces are generated between the gas and the object. The magnitude of these forces depend on the shape of that object, the speed of the object, or in our case, flow around the object, the mass of the gas in the flow field, and on two other important properties of the gas, the viscosity and the compressibility of the gas. To properly model these effects, aerodynamicists use similarity parameters, which are ratios of these effects to other forces present in the problem. If two experiments have the same values for the similarity parameters, then the relative importance of the forces being correctly modeled. This is where Reynolds number becomes very applicable for the aerodynamic world. A comparison between the density, velocity of the flow, length of the test section, and dynamic viscosity can allow scaled model tests in wind tunnels to occur, since the dimensionless Reynolds number of the model can be applied to a full-scale scenario.
So before we start cracking down any numbers, we should make some assumptions to make our calculations easier. So we first assume the flow is steady, that way we don't have to deal with an accelerating flow. We also assume that it's incompressible, that way we have a constant density. In order to calculate our density, we also need a temperature, which we will make constant in this case. So we assume we have an isentropic process. We also assume we have ISA conditions. On the day of the test, the pressure was about 1,000 hectopascals, the temperature was about 21.7 degrees Celsius, and thus our density was about 1.185 kilograms per cubic meter.
A 3-foot-long cylinder with 6 1/4 inch diameter was set to cover the full width of the wind tunnel. There are 24 ports total around the cylinder, spaced at 15-degree intervals, with port 13 being oriented perpendicular to the flow. Instead of all ports being in line with each other, they form a spiral around the cylinder as to not induce turbulences on the neighboring ports. This allows for more accurate data readings. Before testing began, ambient conditions were collected via a virtual weather station present in the control room of the wind tunnel. This data was imported in a lab view to calculate density for the current conditions. The wind tunnel was run at two different RPM values, 310 and 650, which correspond to 13 and 23 meters per second, respectively. Once the flow in the test section stabilized at both velocities, data was taken. The pressure sensors recorded 200 data points over a span of 30 seconds, and two different data sets were taken at both RPM values to ensure the validity of the data. Using the pressure and velocity data gathered, coefficient of pressure, coefficient of drag, and Reynolds number all were calculated. For our second run of testing, we added sandpaper strips, also known as trip strips, between ports 8 and 9 and ports 15 and 16. These strips of sandpaper were intended to create turbulent flow and energize the boundary layer in order to allow it to remain on the cylinder for a longer period of time before separating. We then ran the wind tunnel at 13 and 23 meters per second again, while still allowing for airflow to stabilize before collecting data. Once again, 200 data points were collected at each velocity, with the test being conducted twice at each velocity. After running the wind tunnel for both velocities, with both a smooth cylinder and with sandpaper strips attached to the cylinder, we began to put smoke through the wind tunnel while illuminating the smoke with a laser to aid visualization of the airflow around the cylinder. The laser was positioned in two different orientations, perpendicular and parallel to the cylinder. When the light is perpendicular to the cylinder, it illuminates the flow of smoke over the cylinder, allowing for easy visualization of where the flow separates. With the light parallel to the cylinder, it allows us to view the smoke before contact with the cylinder, assuring us that the flow in the wind tunnel was turbulent even before interacting with the cylinder. The wind tunnel was run at 3 different RPM values for FlowViz, 100, 150, and 200. Smoke was injected through the diffuser using a standard smoke machine using a 3D printed nozzle with a slit in it. The height of the smoke was adjusted to assure that the flow being visualized crossed over the cylinder. A first round of testing was conducted with the sandpaper strips still attached. After this run of testing, the sandpaper strips were removed and the test was conducted again at the same RPM values. It's important to note that data was not collected for analysis during this flow visualization.
Now the videos of flow have a certain order with respect to the RPM. Our first run was 150 RPM with no sandpaper. The following video is 150 RPM with the sandpaper. Next one was run at 100 RPM with no sandpaper. The last one was 150 RPM again with sandpaper.
As part of our data collection, we took two plots of coefficient of pressure versus angle on the cylinder at the two different speeds. Our coefficient of pressure plots shown here clearly display the effect of the cylinder on the flow based on the shape of the plot. For both test speeds, the coefficient of pressure is highest at the point where the port is normal to the flow, which is where theta equals 0 degrees. This is because at this point, port 13, the static pressure is equal to the stagnation pressure, which makes the coefficient of pressure equal to 1. On either side of the cylinder, the coefficient of pressure drops as expected. Our plots have mostly the same shape as the expected curve of the coefficient of pressure over the whole cylinder. The differences are due to port 7 being broken, resulting in it only reading a single pressure value and creating a large erroneous spike in the data. Port 5 is also partially broken, resulting in a smaller spike to the left of the port 7 spike. The negative coefficient of pressure on either side is due to the ports present on the back side of the cylinder. Assuming a temperature of 15 degrees Celsius and therefore using a constant dynamic viscosity, we calculated the Reynolds number for each of the two velocities. Both of them are on the order of 10 to the 5 or 10 to the 6, with the first one being around 700, 800,000 and the second one being around 1.4 million for velocity at 23 meters per second. This means that we are seeing fully turbulent flow around the backside of the cylinder. Because the Reynolds number is significantly greater than 10 to the 5th, 100,000 on both cases. However, the run at 13 meters per second with 700,000 Reynolds number is closer to the transition stage between laminar and turbulent than the 23 meters per second case. In order to estimate the Strouhal number, we used an iPhone 6 to record video at 60 frames per second while recording the airflow coming off the back of the cylinder during the flow visualization exercise. We were able to get a clear estimate of the shedding frequency, around 10 Hz, at a fan speed of 100 RPM. Since this corresponds to an airspeed of around 4 meters per second, and the characteristic length was just under 16 centimeters, being the diameter of the cylinder, we were able to calculate the Strouhal number as frequency times length divided by velocity, which came out to be just under 0.4. The Strouhal number is directly tied to vortex shedding and is generally used in momentum transfer, von Karman vortex sheets, and unsteady flow calculations. This high of a Strouhal number indicates a high amount of turbulent flow and vortex shedding coming off the cylinder.
From the pressure data that was collected from the cylinder, a drag force was able to be calculated. If we look at the drag force at 13 meters per second with no boundary layer modifications, we see that the force is approximately equivalent to 16 newtons. If we look at the drag force at approximately 23 meters per second, once again without boundary layer modifications, we see that the force is approximately 52.5 newtons. Now, this is clearly not a linear relationship, but it can be shown as a relationship where the drag force increases in a proportional manner to the square of the airflow velocity. Also, it should be noted that both of these drag forces were calculated as the average over the two trials. After adding sandpaper, forces were calculated again via the same pressure method. And what we can see that the drag force at approximately 13 meters per second, this time with the modification, is approximately 15 newtons. We can see that the drag force at 23 meters per second, with the modification, is equivalent to approximately 46.5 newtons. Now, once again, both these drag forces are averages over the two trials, but it's clear to see that the boundary layer trip decreases the total drag force on the cylinder. Once again, this is not a linear relationship, and it does follow the same proportional relationship that we noted previously. but this is the same concept that golf balls will use. Golf balls, of course, have dimples, which creates a thin layer of turbulent flow over them, allowing for significantly more consistent flow, more reliable flight, and better flight characteristics because of that. This is the same feature that can be shown from using the strips to trip the boundary layer. This energizes the flow, it makes it more turbulent, but it allows it to stick to the cylinder better, which allows better flight characteristics. Now, with the drag force calculated for both different boundary layer conditions at both different velocities, we can calculate a drag coefficient. The drag coefficient is the ratio of 2 times the drag divided by the density of the air multiplied by the surface area of the cylinder multiplied by the velocity of the air to the second power. We see that at 13 meters per second, with no boundary layer modifications, the smooth cylinder, the coefficient of drag is 1.59. When the sandpaper strips are added, turbulent flow is introduced back in, the energy increases, which means the velocity increases. This drag coefficient then becomes lower to 1.27. This is also mimicked in the 23 meter per second test, where the smooth cylinder has a coefficient of drag of 1.45, where the cylinder with the sandpaper strips attached has a coefficient of drag of 1.28. There were only 2 major sources of error throughout our entire test, and they were both present within the wind tunnel. Port number 7 on the cylinder was broken, resulting in inaccurate readings that cannot be trusted whatsoever. Port number 5 also gave out bad data as well, but not to the degree of number 7. Both of these can be clearly seen in the CP versus theta testing conditions, both of those plots. Those are the clear spikes on the left side of the graph. We know they are incorrect, and they should follow the theoretical guide, but they are noted as errors here for that exact purpose.
Before concluding the lab, we had to do a bit of procedures after the testing. So first you want to make sure you have all your data saved. You don't want to open your file and realize that you got the wrong data or no data at all. After you make sure that you have your data, we set the turbine to 0 RPM and then we turn it off. After that, it's just simple. It's putting everything away and cleaning up after any mess the wind tunnel left over. Once everything's set, you can take off the signs off the doors and you're free to open the doors.